logarithmic properties. Objectives: relate the properties of exponents to those of logarithms and use the properties of logarithms. Properties of logarithms. First, let's recall the properties of exponents. X to the 12th times x to the 5th is equal to x to the 12 plus 5, which is x to the 17. This means when we are multiplying numbers of the same base, we add the exponents. Now, inversion gives us the properties of logarithms. The product property of logarithms states that the log base b of x times y is equal to log base b of x plus log base b of y. This is a property that you can use forwards or backwards. In short, what it means is if we have a product in our argument, we can write this as two separate logs being added. Also, if we have two separate logs of the same base that are being added, we can write it as a single log and multiply the arguments. The following demonstrates the product property of logarithms. Using your calculator, verify that log of 2 plus log of 5 is equal to the log of 10. You can do this on your regular scientific calculator because the log button there is base 10. Now, using the product property of logarithms, we can see that something like log base 2 of x cubed is equal to the log base 2 of x times x times x. Now, using the product property of logs, we can see that this is log base 2 of x plus log base 2 of x plus log base 2 of x. So, how many log base 2 of x's do we have? We can see this is equivalent to 3 log base 2 of x. So, log base 2 of x cubed is equivalent to 3 times log base 2 of x. This brings us to the power property of logarithms. Log base b of x to the y is equal to y times the log base b of x. Again, you can use this property forward or backward. So the log base b of x is also equal to the log base b of x to the y. Now, using the logarithm and exponent properties we know so far, we can manipulate an expression such as the following. Log base 7 of x over m. Our exponent properties tell us that this is equivalent to log base 7 of x times m to the negative 1. Now, using the product property of logarithms, this is equivalent to log base 7 of x plus the log base 7 of m to the negative 1. Now, our power property of logs says that this is equivalent to log base 7 of x minus log base 7 of m. This brings us to the quotient property of logarithms. Log base b of x over y is equal to log base b of x minus log base b of y. Remember that this property can be used backwards as well. The log base b of x minus the log base b of y is equal to the log base b of x over y. Now, just a caution, this would be an improper way to use the quotient property of logarithms. The log of 15 minus the log of 28 is not equal to the log of 15 over the log of 28. If you wanted to use the quotient property of logarithms, this should be equal to the log of 15 over 28. Notice the single log and only the arguments have been divided in the quotient property of logarithms. You can verify this in your calculator as well, that these two expressions are in fact not equal. Now, using log base 3 of 5 is approximately 1.464975352, and the log base 3 of 2 is approximately 0.63092975. Let's find an approximate value for the log base 3 of 10. I know that the log base 3 of 10 is equal to the log base 3 of 5 times 2. My product property says that this is equal to the log base 3 of 5 plus the log base 3 of 2. Now I can put each of these quantities into my calculator and add them to get my approximate value for the log base 3 of 10. And I get an approximation of 2.0959 after I've added those numbers. Now you can try in your calculator to take 3 to the exponent that you just found, and you'll see that it does get very close to the number 10. One technique that proves to be very useful for us with using properties of logarithms is the ability to expand and combine logarithmic expressions. Here, I'm going to expand. When we say expand, this means to get rid of products and quotients in the argument and exponents on the arguments. So here I have log of x to the 4th times y to the 12th divided by z cubed. This is going to be the log of x to the 4th plus the log of y to the 12th minus the log of z cubed. Now, I've gotten rid of my products and quotients in the argument. I need to get rid of the exponents now. So I use my power rule. This is equivalent to 4 log x plus 12 log y minus 3 log z. For this problem, log base 7 of the cube root of x plus y, we need to first start by changing this cube root to a 1/3 power. So this is equal to log base 7 of x plus y to the 1/3. Now remember, expanding these logarithms means that we're going to get rid of the products and quotients in the argument and exponents on the argument. So we'll use the power rule and move the 1/3 in front to be the coefficient of the log. Now we don't have any more things to do. We don't have products or quotients in the argument, and we took care of the exponent on the argument. So we're finished. Here I have the natural log of x squared times the square root of x plus 1 over 2x minus 5. So we could start here by rewriting that square root as x plus 1 to the 1/2, and then I have my 2x minus 5 in the denominator. Well, this will be natural log of x squared plus natural log of x plus 1 to the 1/2 minus natural log of 2x minus 5. Okay, the only thing left to do now is to take care of those exponents on the arguments. So my natural log of x squared becomes 2 natural log x. My natural log of x plus 1 to the 1/2 becomes 1/2 natural log of x plus 1. And then there's nothing we can do with that last log. We just copy it back down. And at this point, we are fully expanded. Here I have log base 2 of the square root x to the 5th over y cubed z to the 4th. So I'm going to change the square root to be rational exponent form instead. And that means that's all going to be to the 1/2 power. So this means I have 1/2 log base 2 of x to the 5th over y cubed z to the 4th. Now I can go ahead and start breaking this up because I have products and quotients going on. So this is going to be a 1/2. I need to make sure that this is multiplying everything that follows. 1/2 log base 2 of x to the 5th minus log base 2 of y cubed and minus log base 2 of z to the 4th. Yes, this is going to be a negative because that z to the 4th is in the denominator. Now I can go ahead and move those exponents on the arguments down to be in front of the logs, each of the logs individually. So I have 1/2 in front of the whole thing, 5 log base 2 of x minus 3 log base 2 of y minus 4 log base 2 of z. And then I can go ahead and multiply this 1/2 through if I wanted to. Give it a little bit better look because we don't have square brackets left then. This would be a 5/2 log base 2 of x minus 3/2 log base 2 of y minus 2 log base 2 of z. On this one, I have log base 3 of x squared minus 9x plus 14 over x squared minus 4. Now, there are no properties for logarithms that I can apply at this point. I have to be able to have products, quotients, exponents on the argument, so I need to go ahead and get this factored first. This would be a log base 3 of x minus 2, x minus 7, and then the denominator is going to be x plus 2, x minus 2. Now I have this common factor in the numerator and denominator that can be removed. So this is log base 3 of x minus 7 over x plus 2. Now I can separate that into two separate logs. Log base 3 of x minus 7 minus log base 3 of x plus 2. Now the interesting part of this is if you had not removed the x minus 2 as a common factor in the numerator and denominator and just went ahead and write each term, you would have 4 log base 3 terms, then you would have a positive log base 3 of x minus 2 and a negative log base 3 of x minus 2, and they end up canceling each other out, and you'd be left with this in the end anyway. Here we want to practice combining logarithms. So we're getting this to where we have a single log of some expression. So I have here the log base 2 of x minus 3 log base 2 of m. For me to be able to get these combined, I need to get rid of this coefficient in the front. So I'm going to use my power rule in reverse. This will be log base 2 of x minus log base 2 of m cubed. Now that I have two log base 2's that are being subtracted, I can write this as a single log base 2 where the positive log argument is in the numerator and the negative log argument is in the denominator. Here I have 5 log base 3 of x squared plus 2/3 log base 3 of y minus log base 3 of z minus 2 log base 3 of w. Again, I'm going to start the same strategy, getting those coefficients that are in front to be the exponent on the argument. So using the power rule in reverse. This is equal to log base 3 of x squared to the 5th is going to be x to the 10th plus log base 3 of y to the 2/3 minus log base 3 of z minus log base 3 of w squared. Now that I have 4 separate logs here being added and subtracted with no coefficients, I can go ahead and use my product and quotient rules to put them all together. So I'm going to have a single log base 3 of, here I'll put my x to the 10th, and my y to the 2/3 is going to be a cube root of y squared. And this is a negative log base 3 of z, so that argument is going to go on the denominator, and another negative log base 3 of w squared, so the w squared is going to end up on the denominator. Here I have 3 times the quantity of log base 2 of 7 plus log base 2 of m minus log base 2 of 8. There are a few ways you could go about doing this. You could go ahead and distribute this 3 to both of those log terms, but I'm going to go about it a little bit differently. I'm going to go ahead and combine the logs that are inside the parentheses so that we have 3 times the log base 2 of 7m. And then I have my minus log base 2 of 8. Now, 3 times the log base 2 of 7m is going to be the log base 2 of 7m cubed minus my log base 2 of 8 is actually 3. So we can leave it right here, and that would be our final combined logarithm.